form of tankers. Okay. So when these under pressure, when under pressure, the material of which they are made is subjected to a loading from all directions. So although this is the case, the vessel can be analyzed in a simpler manner, provided it has a thin wall. Okay. So in general, thin wall refers to a vessel having an inner radius to wall ratio of 10 or more. Actually, you can only turn a particular vessel into thin wall pressure vessel if the the inner radius, okay, the inner radius of the pressure vessel towards the thickness has a ratio equal to, okay, or greater than 10. So then and only then you can term that particular vessel as a thin wall pressure vessel. Okay. So specifically, when R by T is actually equal to 10, the results of a thin walled analysis will predict a stress that is approximately 4% less than the actual maximum stress in the vessel. Okay. So remember that if R by T is actually equal to 10, so the results of a thin wall analysis will predict a stress that is approximately 4% less than the actual maximum stress in that particular vessel. Okay. So for larger R by T ratio, this error will be even smaller. If you increase this value of R by T, so this error of 4% is going to become decrease. Okay, it is actually going to furthermore decrease if you increase this value of R by T ratio. It means that your calculation will go towards accuracy and you will get accurate results regarding the stresses involved in the calculation of thin walled pressure vessels. So when the vessel is thin, the stress distribution throughout its thickness will not vary significantly, and so it is assumed uniform or constant. Okay, so if the pressure vessel is actually thin, so the stress variation throughout its thickness will not vary that much, and it is going to be assumed that the stresses are actually uniform or the constant that are acting on this particular vessels. Okay, so the first type of vessel is actually the cylindrical vessel. Okay, the first type is actually the cylindrical vessel. So whenever a cylindrical or shell or vessel is subjected to an internal pressure, its walls are subjected to tensile stresses. Okay, so if these stresses exceed the permissible limit, the cylindrical vessel is likely to fail in the following two different types of ways. Okay, what is the first type of failure? It may split up into two troughs. Okay, it may split up into two troughs. Let me correct the spelling of the trough. Oh, into two troughs. Okay, so uh, let me let let me first erase this line so that I will be easily able to draw the figure now. Okay, let me do it again. Okay, so let us suppose, as I first particularly explained, that if, for example, if we have a thin walled vessel. Okay, if this is a thin walled vessel actually. Okay, this is a thin walled vessel, and stresses are applied on the walls of this vessel internally. So what is going to happen that the walls of this particular vessel is going to experience the tension force. Okay, tension will be applied on these walls. So what is going to happen? It is going to fail in two different types of manners. First is that it may split up into troughs, and the second one is that it may split up into two cylinders. Okay, it may split up into two cylinders. So what is the first type of failure? It might feel like this. See, for example, if I'm drawing this is the first type of failure, that it is going to split it into two different types of troughs here, like this. Okay, it is going to split it into two different types of troughs like this. Okay, so this is the first type of failure that it might undergo. It is going to split up into two different types of troughs. Okay, and this, what is the second type of failure? The second type of failure is that it may split up into two cylinders like this. For example, this is the first part of the cylinder. Okay, this thin walled cylinder, and let us suppose this is the second part. It is like this. Okay, I've actually drawn this a bit bigger, but these are actually equal in size. But I hope that this is going to get you to understand the concept that whenever a cylindrical shell or vessel is actually subjected to an internal pressure, its walls are subjected to tension, and it may split up into two different. It may undergo into two different types of failure. The first is that it may split up into two different types of troughs, or it may split up into two different types of cylinders. Okay. So when a cylindrical shell is subjected to an internal pressure, its walls are subjected to tensile stresses. Okay, so two types of tensile stresses are possible. The first type of tensile stresses, according to this analogy, is circumferential or Hopf stresses. Okay, this is called circumferential or Hopf stresses. This is actually the type of failure which is actually occurring because of the circumferential or Hopf stresses. Okay, and the second one is actually axial or longitudinal stresses. Axial or longitudinal stresses. So you can see here that this is the second type of example. Okay, this is the this one is actually the axial or the longitudinal type of stresses. Okay, so these are some two different types of stresses due to which your cylinder is going to experience two different types of failure. The first one is the circumferential or Hopf stresses because of the circumferential stresses, because what is happening that the stresses are actually applied at the circumference of this particular hollow shaped cylinder, and it actually splits it up into two different types of troughs here. Okay, and here in the second example, as the stresses are actually applied on the longitudinal direction of this particular cylinder, so it is going to split up into two different types of cylinders here. Okay, so let us first study the example, and let us first derive an equation for the circumferential stresses that are actually occurring in the cylindrical circumferential stresses. So let me first write it down. Okay, so let us suppose that we have a cylinder, a thin walled cylinder. Okay, we have a thin walled cylinder, and to this thin walled cylinder, what is actually happening that it has been split up into two equal parts, that is xx. And now what is actually happening that internal stresses are actually applied to the circumference of this particular cylinder. This is actually pressure P. This is the small thickness T, and this dimension is actually the total this sorry, not this one. Let me rub this out. This I'm actually going to write down the diameter of this particular cylinder. So okay, so this dimension, this internal dimension is actually the total diameter of this hollow cylinder. Okay. Now, because of circumferential stresses, what is actually happened? It has actually split up into two different hoops. So I'm going to draw one hoop that is like this. Okay, it has been split up into two hoops. So one hoop is having the shape of like this. This is the, you can see that this is the diameter D of this cylinder. Okay, the pressure is being applied here on the internal walls of this particular cylinder, and you can see that that significant changes in the thickness, significant changes in the thickness of the cylinder can be actually observed here. Okay, so as a result of circumferential stresses, the cylinder has a tendency to split up into two different types of troughs. Okay, so let us suppose that L is equal to the length of cylindrical vessel. Okay, and now D is equal to diameter of cylindrical vessel. Okay, and P is equal to intensity of internal pressure. Okay, P is actually equal to the intensity of the internal pressure. And in simple words, we can say that P is actually equal to the pressure that is applied at the internal surface of this particular cylinder. Okay. Now, now let us write down the value of stresses. So let us say that sigma 1, okay, let us say that sigma is actually the circumferential, okay, or the Hooke stress. This is the second name for this stress is also equal to Hooke stress. So it is equal to the circumferential or the Hooke stress in the shell slash vessel material. So the bursting force, the bursting force along the diameter of this vessel is equal to intensity of pressure multiplied by the area. Okay, so the intensity of pressure here, I have written down that intensity of pressure is equal to P, and the intensity and the value of area is equal to the diameter multiplied by the length. As you can see that this internal pressure is actually being applied to the diameter. Okay, it is being actually applied to the diameter of this particular of this particular vessel, and this whole pressure is actually applied throughout the length and throughout the diameter of this particular vessel. So the area which we are actually going to take, this is the area. This shaded area is the area on which this particular pressure is going to be applied. Okay, this is a shaded area on which this particular pressure is applied. So that is why I'm multiplying here the value of area here to get the intensity, the bursting force that is actually acting along the diameter of this particular vessel, and that is equal to pressure multiplied by diameter of this particular vessel and multiplied by the length of this vessel. Okay, so what is going to be the resisting force here? Okay, now the resisting force here is going to be equal to we all know that whenever there is an action applied over the body, there is always a reaction. So here there is a resisting force also acting upon this particular stress so that this material does not deform. The resisting force is actually equal to the stress, okay, multiplied by the area, and that is equal to 2 into uh, 2 into sigma 1 into TL. Okay, now for equilibrium condition, for equilibrium condition, summation F equal to 0, 2 into del 1 into T into L is equal to P into D into L. So this value is going to be equal to P into D into L divided by T into L. Okay. Now as you can see that L is actually common here in the numerator and the denominator, so both of them are going to be cancelled out, and we will get this as P into D divided by 2T. Okay, and as G by 2 is actually equal to the radius of this particular cylinder, so in terms of radius, if you want to actually write this formula, you can write it as P into R, okay, divided by T, where R is actually equal to the radius of this cylindrical vessel. Okay, so these are the general formulae that can be used for calculation of the circumferential stresses or the Hopf stresses that are actually developed in the cylindrical pressure valves. Okay, now next we are going to calculate. Let us move on towards the next slide. Now next we are going to actually calculate the axial or longitudinal stresses. Okay, the axial or longitudinal stresses. So as we studied earlier, that axial stresses actually are the type of stresses that actually occur along the axis of the particular cylinder. Okay, so this actually happens when when the stresses are actually applied to the longitudinal to the longitudinal section or along the length of that particular cylinder. So you can see here that let me actually draw the figure. It will be much more easier for you to understand like this. Let us say that I am drawing the figure of a split cylinder here. Okay, I'm going to draw a figure of a split cylinder here. This is a thin walled pressure cylinder here now. And you can see that the pressure is actually applied along the length of this pressure is actually applied along the length of this particular cylinder. Okay, this is here, this is the thickness of this particular cylinder. You can see that this is the thickness, and this particular dimension is actually equal to the diameter of this particular cylinder here. Okay, so what actually is happening that this force is actually tearing away the cylinder into two equal parts. So I can say that the total torn away, or let us suppose if I write it down simply, let us suppose if I want to write it down much simpler in English so that you can be able to understand it. Actually, torn is the second form of this verb. So let me first use the first form, which is actually uh, used in the common in total tear away force acting longitudinally is equal to pressure multiplied by area. Okay, so it is equal to P into pi by 4. This is equal to, this is actually equal to pi by 4 d square. Okay, so total resisting force, the total resisting force is equal to sigma 2 into pi d into t. Okay, so for equilibrium condition, if we apply this equilibrium condition, pi dt is equal to p into pi by 4 d square. Okay, so we will get here the value equal to that sigma 2 is equal to sigma 2 is equal to p into, this is actually sigma 2 multiplied by p pi multiplied by pi into d into d. Okay, so sigma 2 is going to become equal to p into pi by 4 d square divided by pi dt. So cancelling out the common terms, we will, this equation will be reduced to p into d divided by 4 into d. It can also be written as p into it's equal to half p into d divided by 2t. So as we know that p into d divided by 2t is actually equal to the circumferential stress that is termed as sigma 1 here. So um, if let us suppose that we are going to replace it here, so this is this equation is actually going to become half into sigma 1. So this actually means that the axial or the longitudinal stress is actually going to be equal to half the value of the circumferential or the Hopf stresses that are actually applied on a certain cylindrical shape or body. So, in simple terms, we can say that longitudinal stress in a cylinder is half of the circumferential stress. Okay, so this is the simple explanation and analogy of this particular calculation here, that whenever stresses are applied on alongside the diameter and alongside the length of a particular of a particular cylindrical thin vessel. Okay, so because of these particular stresses, what is going to happen, that two different types of stresses are going to develop in this particular cylindrical type thin walled vessel. The first is the circumferential or hoop stresses, and the second one is the axial or longitudinal stresses. We actually calculated two different formulas for finding out the circumferential stresses and the axial or longitudinal stresses for this particular cylinders. So by calculating, we find out that the circumferential stress sigma 1 is equal to P into P, the pressure of the thin walled cylinder applied toward on the diameter multiplied by the diameter divided by double times the thickness of that particular cylinder. And when we calculated the axial and longitudinal stresses, we obtained the formula as equal to sigma 2 equal to half of P into D divided by 2T, whereas P into D divided by 2T was equal to the circumferential stress. So it was derived that the longitudinal stress is always going to be half of the circumferential stress that is developed in that particular thin walled cylindrical shape. So now, having said this, let us solve an example on this particular problem. Okay. So the problem, what does the problem suggest? Problem की statement जो ठीक है वो notes में आप लोगों को मिल जाएगी, ठीक है? You're going to get this in the notes. Let me explain it here ताकि आप लोगों को ज़रा proper तरीके से समझ आ सके, ठीक है? We are going to save time ताकि आप लोगों को notes में जो है ठीक है मैंने सारी information notes में दी होगी, लेकिन यहाँ पे चूँकि we want to save some time here, so I will dictate the problem here and I will provide you with the solution here. Okay. So a steel penstock of 1 meter diameter and 1 centimeter thickness is subjected to 100 meter head of water. Okay. What is actually happening that you have a steel penstock. आप लोगों ने कभी penstock का नाम सुना है? What is penstock? Penstock आप लोग के पास क्या होती है? Can anybody explain? What is penstock?
टरबाइन तक जिसमें पानी जाती है सर।
Yes, बिल्कुल। आप लोग के पास जो ओवरहेड वाटर जो आप लोग के पास जो डैम्स आप लोगों ने बनाए होते हैं, ठीक है? तो टरबाइन को जो ठीक है पानी पहुंचाने के लिए जो आप लोग के पास जो पाइप इस्तेमाल की जाती है, that particular pipe is actually known as the penstock. So they are actually saying that you have a penstock. Okay, this penstock is actually made up of steel. Okay, the diameter of the penstock is actually equal to 1 meter. Okay, it is having 1 meter diameter, and the thickness of this particular penstock is actually equal to 1 centimeter. So if you want to convert the diameter into centimeters, it is going to become equal to 100 centimeter. Okay. So let us calculate the now what is actually being required of this penstock. We are going to calculate the Hopf stress and the longitudinal stress here. Okay, the Hopf stress, okay, is required, and the longitudinal stress is actually required in this particular problem here. Now the height of this penstock is also given. Okay, the height of this penstock is actually equal to 100 meter, and when we convert 100 meter into centimeter, is going to become equal to 10,000 centimeter. So we actually converted this into centimeter in order to keep the units for the problem consistent over here. Now, as you can see that let me draw the figure of the penstock. Let us suppose that this is the penstock, okay, which is actually providing water to the turbine. Okay, the height of this penstock is given as equal to 100 meter. Okay, now the diameter of this is actually equal to 1 meter, and the thickness of this particular penstock is equal to 1 centimeter here. Okay, now here the water pressure that is actually applied on the walls of this penstock, as water is going to travel in the walls of this particular penstock, it is going to apply pressure on the walls of this particular penstock. The water pressure it is going to be equal to the gamma W multiplied by H. Okay, where gamma W is equal to the unit weight of water, which is equal to 1 gram per centimeter cube, and the height of this particular penstock by the data is actually equal to 10,000 centimeter. So we are going to get the water pressure equal to 10 kilogram per centimeter square. Okay, now let us first calculate the value for the Hopf stress. For Hopf stress, we already know that it is equal to sigma 1, and which is equal to P into D divided by 2T. Okay, and the formula for calculating the longitudinal stress here, the formula for finding out the longitudinal stress is equal to sigma 2, which is equal to P into D divided by 4T. Okay, so let us put the values. You will get as 10 multiplied by 100 divided by 2 into 1, and here we will get 10 into 100 divided by 4 into 1. So we are going to get these values here as 500 kilogram per centimeter square, and this value is going to be equal to 250 kilogram per centimeter square. So hence it is proved here by this particular problem that sigma 1 is equal to the half of the value of the sigma 2 here. Okay, so this is the general explanation of this problem, that both the stresses, Hopf stresses, is actually going to equal to the half of the longitudinal stress of that particular body. Okay, it is going to be equal to half of the longitudinal stress of that particular body. Now let us move on toward the next slide to solve another problem. Okay, the statement of this problem will be given to you in the notes. I'm just going to have explain it to you, and then uh, we will move on towards the next topic. Okay, so a cylindrical pressure vessel has an inner diameter of 4 feet. We have a cylindrical pressure vessel. Okay, and its internal diameter is actually equal to 4 feet. Okay, it has a thickness equal to half inches. Okay, means 0.5 inches is going to be the thickness. So what is actually required we have to determine the maximum pressure it can sustain, so that neither its circumferential nor its longitudinal stress components exceed 20 ksi. Okay, So you have to find out the maximum pressure, okay, the maximum pressure on which both the stresses, the half stress and the circumferential stress does not get exceeded from 20 ksi. Okay, so the maximum stress actually occurs in the circumferential direction. As we know that in this kind of situation, we've already proved that the maximum stress actually occurs in the circumferential direction, because the circumferential stress is actually double the value of the longitudinal stress that is actually going to occur in this particular vessel. So for this purpose now, okay, sigma 1 is equal to P into D divided by 2T. So we are going to get the pressure equal to P equal to sigma 1 into 2T divided by D. So by putting these values, you will get P equal to 20 into 2 into half divided by 4 into 12. I'm multiplying this by 12 in order to convert it into inches, because here this is inches and this one is also in inches. So I'm actually converting it in here. Okay. So it is going to become equal to 0.4167 KSI, and if you convert it into PSI, it is going to become equal to 416.7 PSI. Okay. So now the next value we are going to calculate for the for the longitudinal stress, and for the longitudinal stress, the value is equal to sigma 2 equal to P into D divided by 4T. So the pressure is going to be equal to sigma 2 into 4T divided by D. So here the value of pressure we are going to obtain here by putting the values, we will get value 833.4 PSI. So as you can see here that here the values are not exceeding here from the value of 20,000 PSI. So it means that this pressure that is actually going to be developed in this particular vessel is going to be a safe pressure, and it is not exceeding the value of 20,000 psi. That is actually being the design capacity of this particular vessel here. Okay, so the demand value of both the pressure is actually equal to 416.7 and 833.4, and it is not actually exceeding the value of the design that is actually equal to 20,000 psi. Okay, now we are going to solve another problem on this particular topic here. Okay. So this problem suggests that a tank shown it actually shows a tank here. Okay, so let me draw this water tank. This is the water tank. Okay, in this cylindrical shape, and so it actually has an inner radius of 24 inches. Okay, the inner radius of this tank is actually equal to R is equal to 24 inches, and a thickness of 0.5 inches. It is actually having a thickness of T equal to 0.5 inches. It is filled to top with water having a specific weight of the unit weight of water is actually equal to 62.4 pounds per cubic foot. Okay, this particular tank is actually filled up to the surface from water. It is actually being filled up to the surface from water. Now it is made up of steel having a specific weight of uh, the unit weight of steel is given, and that is and the specific weight of steel is actually equal to 490 pounds per cubic foot. Now we have to determine the state of stress at point A, and the tank is open at the top. Okay. Now here a point A is specified. This is point A. Okay, a point A is given here, and at point A we are going to determine the state of stress here. Okay, we are going to determine state of stress here at point A. This tank is open at the top. The condition is given here. Okay. Now in vertical direction, the walls simply hold up. Okay, so the weight of the tank is in this in vertical direction, the walls actually can actually hold the weight of the tank. So this weight is actually equal to weight of steel is equal to gamma of steel multiplied by volume of steel. So this is going to become equal to 490 multiplied by pi into 24.5 divided by 12 whole square minus pi into 24 divided by 12 whole square. This is actually the the full area of this particular cylinder, and this is the hollow area of this particular cylinder. So we are actually subtracting the hollow area from the full area to get the solid area here. So this the volume of this particular steel is actually going to be equal to this at this point A is actually at 3 feet from the top. Okay, so when we are going to get this value here as three point 777. So we okay, so now let us calculate the water pressure on the tank at level A. So P is equal to gamma W into H. Okay. So it is going to become equal to 6624 multiplied by 3. So we are going to get this value as 1872 pounds per cubic foot, which is equal to 1.3 pounds per this is in foot square. Okay, so it is going to become equal to pounds per inch square. Okay, now we are going to calculate the sigma 1, which is actually equal to the Hopf stress developed in this particular in this particular tank due to water. Okay, it is the Hopf stress that is developed due to water. So P into D divided by 2T. So we will get equal to 1.3 into 2 into 24 divided by 2 into 0.5. So we will get this value as 62.4 psi. Okay, and we are going to get another value sigma 2 equal to the sigma longitudinal, and it is actually occurring due to the due to the weight of the wall. Okay, and this value is going to become equal to 777.7. Let me make this correction here, that this value is equal to 777.7. Okay, this value is equal to 777.7 pounds. So 777.7 divided by pi into 24.5 minus 24, both of them are squared. So you will get this value equal to 102 psi. Okay, so both these values are actually being the type of conditions, the type of loads that are actually applied here at the particular point A. Okay, that point A, which was actually specified here, that we had to calculate the water pressure or the simply the state of stress here at A. So the state of stress here at A, due to the Hopf stresses and the longitudinal stresses have been calculated here. So so these are the answers here that we have obtained by calculating this particular value. Okay, so okay, that is the end of this particular problem here now. So if you have any kind of question you can ask here. कोई सवाल हो तो आप लोग यहाँ पे पूछ सकते हैं, और अगर नहीं तो हम आगे बढ़ जाते हैं. ठीक है, हम आगे जा सकते हैं. If you have any question you can ask here. अगर आप लोगों को कोई क्वेश्चन हो तो आप लोग पूछ सकते हैं यहाँ पे.
नो सर नहीं.
ओके, तो सो कैन वी मूव फॉरवर्ड नाउ? हम लोग आगे जा सकते हैं अभी.
जी सर, आप प्रोसीड करें सर.
सर
जी जी.
sigma 1 is equal sigma 2/2. دا کوم سټرس د سره چې موږ دغه کړی دی एग्जांपल کی
जी हूप स्ट्रेस है, हूप स्ट्रेस.
hoop stress is
हाँ जी.
equal 1 by
which is
1 by
actually
2.
equal to the circumferential stress. इसको circumferential stress भी कहते हैं.
ओके सर.
जो कि आपकी circumference के ऊपर अप्लाई होता है. और ये जो आप लोग यहाँ पे पढ़ रहे नीचे, ये आप लोग के पास कौन सी है, इसको एक्सियल स्ट्रेस भी कहते हैं. ठीक है, और इसको लॉन्गिट्यूडनल स्ट्रेस भी कहते हैं, जो कि आपकी थिन वॉल्ड सिलेंडर के ऊपर यहाँ पर आपके पास अप्लाई हो रहा है. ओके, अब हमारे पास यहाँ पे जो है, ठीक है, अब हमने एक और एग्जांपल यहाँ पे स्टडी करनी है. ठीक है, व्हाट हैपेंड, अब हमारे पास उस केस में हम लोग स्ट्रेस कैलकुलेट करना चाहते हैं कि जब हमारे पास मिसाल के तौर पर एक सिलेंडर क्यूब का जो है, ठीक है, उसका वॉल्यूम चेंज हो गया. ठीक है, उसकी डायमेंशन में चेंज आता है स्ट्रेसेस के एप्लीकेशन की वजह से, ठीक है। तो स्ट्रेसेस की एप्लीकेशन की वजह से उसका वॉल्यूम चेंज हो जाता है, या फॉर एग्जांपल उसकी वॉल्यूम, उसकी डायमेंशन चेंज होती है, ठीक है। तो जब उसकी डायमेंशन आप लोगों के पास चेंज होगी तो उस केस में आप लोगों के पास क्या सिचुएशन होगी, ठीक है। So now we are actually going to calculate that particular example here. So now as we know that by the calculation से हमें पता है कि हमारे पास जो सिग्मा 1 है हॉप स्ट्रेस जो है, ठीक है, उसको जिसको हम लोग हॉप स्ट्रेस कहते हैं, ठीक है। हॉप स्ट्रेस हमारे पास बराबर है P इंटू डी डिवाइडेड बाई 2T, जबकि हमारे पास सिग्मा 2 जो, ठीक है, जिसको हम लोग लॉन्गिट्यूडल कहते हैं, ये हमारे पास बराबर है P इंटू डी डिवाइडेड बाई 4TD, सही है। तब हमारे पास अब हम ये कंसिडर कर रहे हैं कि मिसाल के तौर पर इन स्ट्रेसेस की वजह से हमारे पास वॉल्यूम में चेंज आ गई, ठीक है। तो चेंज इन द डायमीटर, सबसे पहले हमारे पास वॉल्यूम में चेंज किस वजह से, पहले चेंज हमारे पास किस में होगा, डायमीटर में होगा। चेंज इन डायमीटर ऑफ शेल, ठीक है। दूसरा चेंज हमारे पास किस में आएगा, वो हमारे पास लेंथ में आएगा। इट इज गोइंग टू बी इक्वल टू चेंज इन लेंथ ऑफ द शेल, ठीक है। और फिर हमारे पास जो, ठीक है, पॉइजॉन्स रेशो होगी, पॉइजॉन्स रेशो, ठीक है। तो पॉइजॉन्स रेशो जो, ठीक है, वो हम लोग चेंज इन लेंथ या चेंज इन वॉल्यूम में हम लोग इसका इस्तेमाल करते हैं, ठीक है, स्ट्रेन को कैलकुलेट करने के लिए, ठीक है। सो सर्कमफ्रेंशियल स्ट्रेन हमारे पास किसके बराबर होगा, वो हमारे पास, इसको हम लोग लेंगे, इट विल बी टेकन एज E1, और इट इज इक्वल टू change in diameter divided by D is equal to sigma 1 by E minus mu into sigma 2 by E, ओके। अब दूसरा हमारे पास है लॉन्गिट्यूडनल स्ट्रेन का, ठीक है। लॉन्गिट्यूडनल स्ट्रेन हम लोगों ने मालूम करना है, तो लॉन्गिट्यूडनल स्ट्रेन का फॉर्मूला हमारे पास यहाँ पे आएगा change in length divided by the original length, so it is equal to sigma 2 by E minus mu into sigma 1 by E, okay. So it is going to become 2P into D divided by 4 4T into E minus mu into P into D divided by 2TE, okay. So which is equal to P into D divided by 2TE into half minus mu. Now change in length and diameter may be find out from the above equations, ठीक है। change in length और diameter जो, ठीक है, आप लोग ऊपर इक्वेशन से कैलकुलेट कर सकते हैं by multiplying the strain in corresponding linear dimensions, ठीक है। So E1 is equal to change in diameter divided by diameter, so it is going to give you the change in diameter change in diameter equal to E1 into D. So it is going to become equal to change in diameter equal to P into D divided by 2T E into 1 minus mu divided by 2 into D. Okay. So it is going to become equal to P into D square divided by 2TE into 1 minus mu divided by 2. Okay. Similarly, for E2 is equal to change in length divided by original length, it is going to become equal to change in length equal to E2 into L. So this equation is going to become equal to P into D divided by 2TE into half minus mu into L. Okay, and this is going to become equal to P into D into L divided by 2TE into half minus mu. So these are some different equations that are actually going to be calculated for calculating the change in length and the change in diameter whenever stresses are actually applied on this particular vessel. Okay, इसके ऊपर आप लोग अप्लाई करेंगे, ठीक है। तो आप इसके जरिए आप लोग चेंज इन लेंथ और चेंज इन वॉल्यूम आप लोग इसके अंदर जो, ठीक है, आप लोग इसमें कैलकुलेट कर सकते हैं, ठीक है। यू कैन कैलकुलेट देम. So in order to make your life simple and easier, I will first circulate these formulas. ठीक है, मैं इन formulas को circulate कर देता हूँ, ठीक है। इनको मैं सर्कुलर फॉर्म में मार्क कर देता हूँ, ठीक है। और अभी हम एक प्रॉब्लम सॉल्व करते हैं तो आप लोग को इजीली ये प्रॉब्लम, ये आइडिया जो, ठीक है, आप लोग इजीली इसको ग्रास्प कर लेंगे, ठीक है। सो कैलकुलेट द इंक्रीज इन वॉल्यूम इनक्लोज्ड बाय अ बॉयलर शेल, ठीक है। oh sorry, now we are going to calculate the problem is actually suggesting that a cylindrical shaft 3 meter long and 1 meter internal diameter. We have a cylindrical shaft. Okay, हमारे पास एक cylindrical shaft है, ठीक है। इसकी लेंथ हमारे पास कितनी है? इसकी लेंथ हमारे पास होगी 3 मीटर इज इक्वल टू द लेंथ, ठीक है। आपके पास इसकी लेंथ जो है वो 3 मीटर है, ठीक है। और इसकी इंटरनल डायमीटर आप लोग के पास कितना होगा? इंटरनल डायमीटर जो है, ठीक है, इंटरनल डायमीटर की बात कर रहा हूँ, इज इक्वल टू 1 मीटर, ठीक है। और आप लोगों के पास जो इसकी थिकनेस होगी, ठीक है, थिकनेस आप लोग के पास कितनी होगी? थिकनेस आप लोग के पास इज गोइंग टू बी इक्वल टू 15 मिलीमीटर। थिकनेस आप लोग के पास 15 मिलीमीटर होगी, ठीक है। डायमीटर आप लोग के पास इंटरनल 1 मीटर होगा। इसमें आप लोगों ने क्या फाइंड आउट करना है? आप लोगों ने इसके अंदर फाइंड आउट करना है हॉप स्ट्रेस, आप लोगों ने कैलकुलेट करना है, ठीक है। और लॉन्गिट्यूडनल स्ट्रेस जो, ठीक है, वो आप लोगों ने इसके अंदर कैलकुलेट करना है। एंड ऑल्सो चेंजेस इन द डायमेंशन ऑफ द शाफ्ट। और आप लोगों ने जो शाफ्ट की जो डायमेंशंस हैं उसके अंदर चेंजेस मालूम करनी, यानी आप लोगों ने चेंज इन डायमीटर आप लोगों ने मालूम करना है, ठीक है। और आप लोगों ने चेंज इन लेंथ जो, ठीक है, वो आप लोगों ने कैलकुलेट करना है। और अब इसमें आप लोगों के पास इंटरनल प्रेशर की वैल्यू जो आप लोग को दी गई, इंटरनल प्रेशर इज एक्चुअली नॉट गोइंग टू एक्सीड 15 किलोग्राम पर सेंटीमीटर स्क्वायर। और आप लोग के पास ई की वैल्यू जो होगी, ई की वैल्यू आप लोग के पास कितनी होगी? द वैल्यू ऑफ ई इज गोइंग टू बी इक्वल टू 20 इंटू 10 रेज़ टू द पावर 6 किलोग्राम पर सेंटीमीटर स्क्वायर। और पॉइजन रेशो आप लोग के पास क्या होगा? ठीक है, पॉइजन रेशो जो है, ठीक है, द वैल्यू ऑफ म्यू इज गोइंग टू बी इक्वल टू 0.3. So let us solve this particular problem. L is equal to 3 meter, which is equal to 300 centimeter, and D is equal to 1 meter, which is equal to 100 centimeter. Okay, now thickness, we're going to calculate the thickness. Thickness is equal to 15 millimeter, which is equal to 1.5 centimeter. Pressure is equal to 15 kilogram per centimeter square. Okay, kilogram per centimeter square, and the value of E is equal to 2 into 10 raised to the power 6 kilogram per centimeter square. So the value of Hop's stress is equal to P into D divided by 2T. You already know what are the values of P, D and T. So by putting values, we are going to get 500 kilogram per centimeter square. And for sigma longitudinal, the formula is P into D divided by 4T. By putting the values, you're going to get 250 kilogram per centimeter square. So now we are going to calculate the change in diameter. Okay, we are going to find out the change in diameter. The formula for that is equal to P into D square divided by 2TE. Okay, it is going to be equal to 2T into E into 1 minus mu divided by 2. ये फार्मूला मैंने कहाँ से उठाया? ये फार्मूला जो ठीक है मैंने यहाँ से उठाया। सही है जी। तो इसके अंदर आप लोग वैल्यू सपोर्ट करेंगे तो आप लोगों के पास क्या वैल्यू निकल आएगी? इसके अंदर आप लोगों के पास वैल्यू निकलेगी चेंज इन डायमीटर इज इक्वल टू 0.021 centimeter. Similarly, when you put the values in the other formula, that is for change in length, so change in length formula आपके पास है P into D into फॉर्मूला के P into D into L, ठीक है, P into D into L divided by 2TE into 1 by 2 minus mu, ठीक है। तो इसके अंदर जब आप लोग वैल्यूज पुट करेंगे तो आप लोग के पास वैल्यूज आंसर निकलेगा 0.015 सेंटीमीटर। ठीक है जी। So this is the solved example for this particular case, ठीक है। आप लोग के पास इस particular case के लिए जो ठीक है solved example आप लोग के पास आ गई, ठीक है। So that is the end of today's lecture, ठीक है। यहाँ पर हम आज का लेक्चर कंक्लूड करते हैं, ठीक है। इसके बाद हमारे पास टॉपिक है चेंज इन वॉल्यूम ऑफ थिन सिलेंड्रिकल शेल ड्यू टू इंटरनल प्रेशर, ठीक है। इसके बाद हमारे पास जो टॉपिक है वो है चेंज इन वॉल्यूम ऑफ अ थिन cylindrical shell due to an internal pressure, ठीक है जी। तो ये जो टॉपिक है, ठीक है, ये आप लोगों को मैं एज ए रीडिंग असाइनमेंट दे रहा हूँ, ठीक है। नोट्स में आप लोगों के पास गिवन है, इसको समझने के लिए आप लोगों को जो पिछला लेक्चर जो मैंने रिकॉर्ड किया है, ठीक है, वो पहले आप लोगों ने देखना है, उसके बाद आप लोगों को इस चीज़ की समझ आएगी, ठीक है। So if you have any questions, I will answer them in the next lecture. I want you to go through it and inshallah you will understand